Okay, this is the last section in this review, and these are some of the things people struggle with. So it's things we had to do algebraically. So manipulations algebraically, such as proving a function is even, odd, or neither, not just graphically, but by algebra. Finding the inverse of a function algebraically. Proving or disproving two things are inverses of each other. Evaluating combinations and compositions of functions. So there's quite a bit in this section. So let's start out with proving functions are even or odd. Okay, what you have to do is you have to make a chart. You have to look at f of x, you have to look at f of negative x, and you have to look at negative f of x for this function. Okay, and then your indicator. If these first two things match, then that's what makes this an even function. If these second two things match, that's what makes this an odd function. If nothing matches in this equation, in this chart, then your function is neither even nor odd, okay? So let's just work through a few examples. We'll do that in just a moment when we hit it. Combinations of functions. Remember, if you've got two functions, f plus g is adding them together. F minus g is subtracting one from the other. F and this closed in dot, that's multiplication, okay? And then f divided by g is division, okay? Don't confuse. Remember that this is multiplication, and this we'll talk about in a moment. That's composition. Those are two different things. Make sure you keep those straight. So let's take a look at a couple examples of this. If I have f of x, square root of x minus 1, g of x is 2x minus 3, the domain of g is negative infinity to infinity. That's just a line. There are no restrictions. There is a restriction on f of x. It's a square root. So what's under the square root? What's under the square root cannot be negative. So that means x has to be greater than or equal to 1. So the domain is 1 to infinity. So when I multiply f and g together, this is f, this is g. That's what happens when I multiply them together, and the domain is going to be the more restricted of those two values, okay? What happens when I add f and g? That's when I get this expression. Same thing, the domain is the more restricted domain that you see from f. When I subtract them, g minus f, so that's 2x minus 3 minus square root of x minus 1, same thing, the domain is g minus, is the same as the domain of f, 1 to infinity. Now the next one throws a little bit of a wrinkle in. When you have f divided by g, so you see f divided by g is here, but now I have another restriction. Remember, I can never divide by 0. So 2x minus 3 cannot be 0. That means that 2x cannot be 3, or x cannot be 3 halves, okay? So I was already used to the restriction of 1 to infinity. So I had 1 to infinity. That was my domain. But now I just found out that x cannot be 3 halves. Okay, that cannot be part of my solution. So that tells me that the domain of this function has to be from 1 to 3 halves, or from 3 halves to infinity. Okay. Composition. Actually doing this review before I taught this, so I'm hoping you did not struggle with it, but in the past people have. So what does it mean to say F composition G? Remember, this is the F and the little open circle, like the degree sign, F composition G. All that means is F of G of X. So you are going to plug G of X into F of X. Okay, the way we always did this was start with the outside function F. So f of x is 2x, x squared minus 3. Rewrite this with blank parentheses everywhere you see an x. So f of blank parentheses equal blank parentheses squared minus 3. Now, what has to be substituted in there is x plus 5, which is g of x. So everywhere you see that, you'll put an x plus 5, and then this is what you end up with. F composition g is x plus 5 squared minus 3. What about G composition F? So G of X is X plus 5. Rewrite it with blank parentheses. And then now F of X has to get substituted in to this expression. So I get x squared minus 3 plus 5. X squared minus 3 plus 5 is just x squared plus 2, which is the answer there. Now, one thing that was similar but a little bit different is if I ask you for a specific value of a composition, n of m of 6. The way we approach this, n of m of 6, is this way. Go find m of 6 first, okay? So plug 6 into m. You'll get a number. Take that number and then plug that into n. So first thing, what is m of 6? M of 6 is going to be equal to the square root of 6 plus 4. So m of 6 is the square root of 10. Now, I need to find n of that value. So what is n of the square root of 10? That is going to be the square root of 10 squared minus 5. That's 10 minus 5, which is 5. Similar over here, m of n of 12. So start with the innermost function. Go find n of 12. N of 12 is going to be, this is done wrong. So n of 12 is going to be 12 squared minus 5. That's 144 minus 5, which is 139. And then find m of that. So m of 139 is equal to the square root of 139 plus 4. M of 139 is the square root of 143. Okay? So there was a mistake here. So n of 12 is 139. And then we find m of 139. All of this is the square root of 143. I need to go back and correct that in the book. Okay? Finding the inverse of a function. Remember, at its basic definition, an inverse is where your x and y change roles. Okay? So if I'm asked to find the inverse of x cubed plus 1, let's just rewrite it with, instead of f of x, let's write it as y equal x cubed plus 1. Now, let's switch the role of x and y, and then all we have to do is solve for y. So that's where the work comes in this. Solve for y. So to solve for y, I need to get the y by itself. So x minus 1 equal y cubed. To get y by itself, I'm going to need to take the cube root of both sides of that equation. That's solved for y. So now f inverse of x is cube root of x minus 1. Proving or disproving that two functions are inverses of each other. Okay, so if functions are inverses of each other, then you can apply them and the changes that you make will always undo each other. So the way I talked about it in class is f is a function that takes you somewhere. If g is its inverse, then you're going to get right back where you started. So you're going to end up where you started. Or g composition f is equal to x. Okay, so f is a function that takes x and does something with it. Well, g is the function that takes that and really undoes it and gets you right back where you started. So if they're inverses, you have to prove both of these compositions give you x. So in this case, let's just do one of these and we'll do some example. So if I needed to prove that f composition g is equal to x, that's what I have to show. So let's look at the next one. So this is f of x is equal to 4x minus 7. So I'm going to write it with blank parentheses. And what needs to get substituted in here is g of x. So f of g of x is equal to x plus 7 over 4. Okay, now I just need to simplify this. So when I simplify this, I get f of g of x is equal to the 4's cancel. This is x plus 7 minus 7, that equals x. Okay. That's proving f composition g equals x. You also have to prove G composition F is equal to X. And we'll see some examples of this in a moment. Inverses and one-to-one functions. Okay, you should be able to look at a set of ordered pairs and tell if something is a function. It's a function if there are no repeated X values. So yes, this is a function. Okay, so this is a function. Okay, it is one-to-one if there are no repeated Y values, 1, 3, 4, 7. So this function is one-to-one. If it's one-to-one, then its inverse is a function. So a lot of this is just based on definition. Look at the next one. Is this a function? 0, 1, 3, 6. Yes, it is a function. Okay. Is it one-to-one? 1, 1, 4, 7. I see repeated Y values. This thing is not. It is not one-to-one. Therefore, the inverse is not a function. So let's work through that. Went in a little bit of a hurry, but let's work through some problems here. Is x squared plus 2 even, odd, or neither? Okay, so f of x is equal to x squared plus 2. Okay, f of negative x is equal to negative x squared plus 2. Well, negative x times negative x, that's the same as x squared because the negative 1 becomes negative 1 times negative 1 is x. So f of negative x is equal to x squared plus 2. These two things are identical. So this is an even function, and you need to be able to give a reason. It is even because f of x equal f of minus x. Prove whether the next function is even, odd, or neither. Okay, so f of x is equal to square root of x plus 1. Okay. F of negative x is equal to square root of negative x plus 1. Okay, so I've got this. Okay. And then if I look at negative f of x, that just means stick a negative in front of everything on both sides of the equation. Okay. I look at this and none of these things are identical. Okay. So in this case, this thing is neither even nor odd. So it's neither because f of x does not equal to f of negative x, and that is not equal to negative f of x. Nothing is equal. Okay. Prove whether this next function is even, odd, or neither. So f of x is equal to x cubed plus x. F of negative x is equal to negative x cubed plus negative x. So this, think of this as this is negative x times negative x times negative x plus negative x. So the first one, negative, 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 that is just negative x cubed minus x. Okay, so this is f of minus x. So these two guys don't match. Okay, what is negative f of x? So negative f of x just says stick a negative in front of everything you see on f of x. That's negative x cubed minus x. Those two match. So this is an odd function because f of negative x equal negative f of x. Next example, absolute value of x plus 2. F of x is equal to x plus 2. F of negative x equal absolute value of negative x plus 2. Well, think of this. This is negative 1 times x plus 2. Absolute value of negative 1 is 1. This simplifies down to f of negative x is equal to absolute value of x plus 2. And boom, these two guys match. This is an even function. It is even because f of x equal f of negative x. Okay. Okay, finding inverses. Okay, so remember, just rewrite this as y equal 2x minus 11. Switch the role of x and y, and then solve for y. Okay, back up, and then solving for y. Okay, so this is going to be x plus 11 equal 2y. Divide both sides by 2. So you're going to get y is equal to x plus 11 over 2. Now, the other way to think about this is, I mean, when you read this, multiply x by 2 and then subtract 11. What's the backwards of doing that? Adding 11 and then dividing by 2, which is what you see right here. So f inverse is x plus 11 over 2. Finding g inverse. So y is equal to square root of x plus 2. Switch the role of x and y and solve for y. So this is x minus 2 equal the square root of y. This guy gets solved by squaring both sides. So x minus 2 squared is equal to y. So g inverse of x is equal to x minus 2 squared. Proving that two things are inverses. So to prove things are inverses, I have to prove two things. F composition g is equal to x, and g composition f is equal to x. So start with the outside function. F of x is equal to 5x plus 11. So that means that f, just replace it with blank parentheses. This is what f does, okay? I need to plug in g of x, okay? What is g of x? That is x minus 11 over 5. And now I just need to simplify. When I do that, 5 times 5 is 1. This is just x minus 11 plus 11. That equals x, okay? That's half of it, okay? The other thing is g composition f. Start with the outside function. G of x is x minus 11 over 5. Rewrite it with blank parentheses. Now, what gets substituted in? F of x needs to be substituted into g of x. What is f of x? That is 5x plus 11. So this is 5x plus 11 minus 11 over 5, which is 5x over 5, which is x, and I'm done. Okay? And over here, same thing. Prove or disprove these are inverses. So I've got to do f of g of x and g of f of x. So f composition g. So f of x is square root of x plus 1. So just rewrite that with blank. And I'm substituting g of x into that equation. What is g of x? X squared minus 1. So this is the square root of x squared minus 1 and this is not equal to x, okay? So f and g are not inverses. Same thing here, f and g. So f composition g, so this is the f of x is equal to 1 over x plus 2. That means f does this. I need to substitute g of x into f, and g of x is 1 over x minus 2. So this becomes x minus 2 plus 2, which is x. Okay, that's half of it. Now let's go look at g composition f. So g of x is 1 over x minus 2. And I need to substitute f of x, which is 1 over x plus 2. So this becomes 1 over x, which is x. So yes, these are inverses, okay? So these are inverses. Prove the following are inverses of each other. So f, composition g. So f of x is 1 over x plus 1. Substituting in g of x, which is 1 over x minus 1. So this becomes 1 over x, which is x. That's what we want. Now let's look at g composition f. So g of x is 1 over x minus 1, blank parentheses. What gets substituted in is f of x. F of x is 1 over x plus 1. So this is x plus 1 minus 1, which is x. So these are inverses of each other. Find f of g of 0. Okay, so g of 0 is 3 times 0 minus 1, which is negative 1. So that gets substituted into f. So f of negative 1 is going to be negative 1 squared plus 4, which is 5. G of f of 0. So f of 0 is equal to 4, and then g of 4 is going to be 3 times 4 minus 1, which is 11. Find f composition g. Okay, so f of x is x squared plus 4. Just rewrite it with blank parentheses. What gets substituted in is g of x. What is g of x? That is 3x minus 1. So f composition g is 3x minus 1 squared plus 4. G composition f. So g of x is equal to 3x minus 1 with blank parentheses. That looks like this. And then what gets substituted in is f of x. F of x is x squared plus 4. So g composition f is 3 x squared plus 4 minus 1. Algebraic operations with functions, okay? The domain of this function is negative infinity to infinity. There are no domain restrictions. The only kind of domain restrictions are square roots and dividing by 0. This one has no square roots or division by 0. This one has a square root. What is under the square root cannot be negative, okay? So this domain is 0 to infinity. This one has a restriction. What is on the bottom of this fraction cannot be 0. So the domain is every number in the world except for 0. And this is the way we write every number in the world except 0. So find f plus g and state its domain. So f plus g is just going to be 2x minus 1 plus x squared plus 3. I can rewrite this as x squared plus 2x plus 2, and its domain is the same domain as both functions, negative infinity to infinity. F times k, okay, remember these are multiplication, not composition. So f times k is going to be 2x minus 1 times 1 over x. So this is just 2x minus 1 over x. And what is the domain restriction for this? Okay, I cannot divide by 0. So this inherits the domain of 1 over x. So this, every number except 0 is valid for this function. G divided by f, okay? So G divided by f, that's going to be, so G over f is x squared plus 3 divided by 2x minus 1. Okay, my restriction here is what's on the bottom cannot be 0. So 2x minus 1 cannot be 0. 2x cannot be 1. X cannot be 1/2. The way we write x cannot be 1/2 is every number from negative infinity to 1/2, and then every number from 1/2 to infinity. K minus f, okay? So k minus f is going to be 1 over x minus 2x minus 1, okay? I mean, another way of writing that is k minus f is 1 over x minus 2x plus 1. What's the restriction here? The restriction is the same as this one. X cannot be 0. And finally, k composition f, okay? So this is k of f of x. So k of x is equal to 1 over x. So k does this, and then what needs to get substituted in is f of x, okay? F of x is just 2x minus 1. And then what is the restriction? Well, the restriction here is x cannot be 1/2. So the domain here is negative infinity to 1/2 and 1/2 to infinity. So some other operations. Is this a function? So the key to is a function is, are there any repeated x values? There are no repeated x values. It is a function. Is it 1-to-1? I'm looking for repeated y values. The value of 5 is repeated, so it is not 1-to-1. The inverse will not be a function. Looking at G, is this a function? Where are my x values? None of those are repeated, so yes. Is it 1-to-1? Do I have any repeated y values? No. It is 1-to-1. Its inverse will be a function, okay? Looking at the next one here, is this a function? 1, 2, 7, 9, 3. No repeats. It is a function. Is it 1-to-1? 7, 9, 8, 0, 15. No repeats. Yes, it's 1-to-1. Its inverse is a function. What is its inverse? All that happens in an inverse, guys, the x and y change roles. So 7, 1, 9, 2, 8, 7, 0, 9, 15, 3. That's the inverse. The next one, is it a function? Look at the x values, 1, 3, 6, 8. They do not repeat. Find the inverse of 7. Okay, sorry. I was answering the questions from the previous one, sorry. Find h of 1. So when you substitute a 1 in, what do you get? Well, h of 1 is 2. Okay, you plug in a 1, you get a 2. H inverse of 7. So when you switch the role of x and y, if you were to plug in a 7, you would get a 6. Okay, h of 6. Plug in a 6 for x, you should get a 7. H inverse of 5. You plug in a 5 and you should get an 8 on the inverse. And that is it. So that's it for the review packet in the book. This is not everything. You need to make sure you look at all of your quizzes, but this is sort of a good tutorial of trying to kickstart and, in about an hour and a half, teach what we did the entire semester. Okay?